design this mission, what I did is I divided in 8 different segments, and I sized one by one all the segments using the best tool available, the rocket equation, for the most general case, including gravity, drag, and steering losses, and also the surface rotation of the planet. So in the most accurate way possible. And by using the rocket equation, we had to of course, make some trades and make some decisions. And the result that we got is that the best combination of assumptions to make for this particular kind of mission is to use chemical proportion. Well, this was not a final result, to use chemical proportion for all phases. This was my initial assumption because I wanted to go with something that already exists rather than assuming nuclear thermal proportion, which has not been finalized yet, although it exists as a technology. But I wanted to use something that exists now and see how it would work. So chemical proportion, pre-deployed Earth return vehicle, once again to save propellant, to try to obtain the most favorable situation. And in fact, I calculated both the cases with or without a pre-deployed cargo, and using a pre-deployed cargo that leaves one synodic period in advance is actually more favorable. It saves in propellant overall, but I come back to this later. Then I assume the use of in situ resource utilization, and the calculations I made prove that it's better to use the hydrogen that is needed for the SRU plant. It's better to bring the hydrogen from Earth in advance with the pre-deployed cargo rather than either produce it on Mars, because that would imply landing where the water is on the poles, but that requires more delta V, or bring it with the crew, but that also would increase the propellant. So the best solution was to bring the hydrogen from Earth with the pre-deployed cargo. And the next assumption is aero capture at Mars, because for such a mission we cannot have aero braking, because that would take too long, weeks or actually months probably, and direct entry would subject the crew to high G's of acceleration. So aero capture, even though it's never been tried, is the only way to go for this kind of mission. So we must find ways to try to make it work. And I assume the crew of 4 people because the stay time is relatively short. So I don't think a crew should be greater than this. This is just a schematic about the mission. It's like where I assume the use of the Ares-5, although we don't know if it will ever be built or constructed or used, but it was a good example because of its capability to LEO. The nominal performance to LEO of the Ares-5 is 188 metric tons in the best case. So I assumed this capability, and by doing this, the result is the use of 3 launches of the Ares-5 for the cargo mission. The cargo, of course, doesn't use the profile I showed you. The cargo goes on a low energy transfer trajectory because there are no humans on board. So the delta V required for the cargo is smaller. The components launched to LEO are assembled in LEO, and they form a couple of vehicles, the ERV cargo and the surface cargo. The ERV cargo releases the ERV in low Mars orbit. The surface cargo delivers the payload on the surface, which is made by a surface-habited ISRU plant and additional equipment. At the next synodic period, the crew launches using 4 launches of the Ares-5. This higher number is due to the higher propellant needed for the mission. So it takes a lot of propellant, probably about 80% of the total initial mass to LEO. As we will see also later, 80% is propellant. The crew travels to Mars. The Mars descent vehicle, which is part of the Mars Transfer Vehicle, or MTV, descends to Mars. The crew stays 25 days, and at departure date, the crew uses the top part of the Mars descent vehicle. So there is not an ascent vehicle waiting for the crew on Mars. It's the same vehicle that brings the crew on the surface that takes them also back to orbit. And this was also the result of a trade I made, and this actually saves propellant. So probably the most harsh requirement to be able to do this is to be able to find the right method to transfer cryogenic propellants. In this case would be LOX and methane produced on Mars. We need to transfer them from the ISRU plant to the ascent vehicle somehow, because the propellant is waiting on Mars and the ascent vehicle has an empty tank, so we need to do this transfer. And this also is another problem. The crew rendezvous in low Mars orbit with the ERV, goes back into Earth transfer trajectory. And at Earth, we can perform a direct entry, because at Earth, the atmospheric density, of course, is higher. So we don't have the problem we have on Mars, and on Earth we can do direct entry just like the Apollo mission did. This briefly is just the aero capture sequence, just to show you how it was designed. The crew arrives on an hyperbolic arrival trajectory and captures in an elliptical orbit with perihelion at 45 kilometers. This is necessary to capture by using the atmosphere. And then the crew performs perihelion race burn at apoarion and circularizes. And after this, the orbit burn is performed. So this is a typical aero capture sequence. This table shows the results more in detail. Okay, 5 minutes. More in detail for the crew mission. I think the most important result here is the initial mass in LEO, which is the top left result. The initial mass in LEO required for the crew mission is 662 metric tons, which is roughly 60% more than the mass of the space station. So we're talking 1.6 times the International Space Station for this mission. So it's not crazy, it's not 100 times the space station. We're talking the order of less than 2 times. So it's something that is within reach, I think. When we consider the whole results for the whole mission, including also the cargo mission, then we need to add about 500 metric tons more. So the total mission, including the 25-month time span for the whole mission, would be about 1,100 metric tons. 500 for the cargo mission and 660 for the crew mission. We're talking about 3 times the space station for the whole mission. And what we would need is 7 launches of the Ares 5, as we said, and assuming the Saturn V was still with us, we still could use it, we would need 11 launches of the Saturn V to do this mission. And by the way, the total number of launches of the Saturn V in its history, I think, was 12. So this is comparable to that. Although I have to say, NASA DRA 5 considers several scenarios, but still, I think it leans still a little more to the conjunction class mission. why I put this case, although you have to say consider 7. The total round trip time is about 960 days for the NASA missions, and 407 for this kind of mission. These are other terms of comparison. I'm just going to talk about the highlighted ones. You can see the class of the vehicles that are assumed by NASA and what I assumed. There are several ranges. They go from higher to lower than what I assumed. And the total number of launches for our mission is comparable to the total number of missions of NASA. Although NASA considers the use of nuclear thermal reactor propulsion, at least for the trans-Mars injection stage of the mission. And once again, we didn't want to assume this. We wanted to do something that already exists to make it as realistic as possible.